everyone. In this lecture, or let's say this is a tutorial, we are going to solve some mathematical problems, some numerical problems, right? So here and there during the class itself, we have solved some problems, but I thought that some more examples are going to help you. So in that case, what we are going to do is as follows. Now you can pause the video and or take a screenshot or something like that. Go through these problems and then I'm going to show you how to solve them. Okay, so now we are going to briefly or quickly solve our numerical problems. So you can see the problem statements on the slide in the beginning. This is the one on radiocarbon. Okay, so you already know that what is the radioactive decay law. We also discussed, we also solved a little problem during the lecture actually. So the decay law basically states n equals n0 e power minus lambda t. Lambda is your decay constant. N is the number of unchanged atoms at any given time t. So unchanged at any given time t. And N0 equals the number of total number of atoms at any given time t. So number of atoms at t. Okay, and lambda is your decay constant. Okay, so first of all, let's go back to our simple solution t half, because we have the value of t half given here. That is, what is it, 5745 years. So t half basically equals 0.693 by lambda, that you already know. So we can find the value of lambda from here. 0.693 divided by 5745. Now again I will do 365 days into 24 hours into 60 minutes into 60 seconds. So the value comes out to be something like 3.83. You can check my calculations again. I have done it very quickly. Minus 12 per second. Okay, now our next task is to find out the weight of barium carbonate. So we know one thing, that is the number of atoms that are decaying is sort of proportional to the total number of atoms that are present, right? So number of atoms decaying proportional to total number of atoms present, which basically means that what do we have here? We have a simple first order reaction. So now what we can do is we can use a simple expression for first order reactions, and that would be equal to your lambda n. And now the lambda n can be expressed in terms of weight and molecular weight. So we have, let's say weight is W, so we need to calculate this, and that will be divided by the molecular weight of barium carbonate. And if we need to find the number of atoms, what do we need? We need one more something else, which is the Avogadro's constant. So 6.023 into 10 power 23 to find the total number of atoms. Okay, this gives me a value 1.16 into 10 power 10. Now multiplied by W, because we don't really now know the value of W. However, what do we know here? We know that the activity that we need to get is 1 millicurie. Now interestingly, what is 1 millicurie? This actually equals 3.70 into 10 power 7 decays per second. So 1 curie equals 3.70 into 10 power 10 decays per second. So remember, since we are talking in terms of decays, so now it will be 10 power 7 and not 10 power 13. Okay, so now this value 1 millicurie is what is equal to our minus dn by dt. So from here we can now find the value of W. So W will be equal to what? 3.70 into 10 power 7 divided by 1.16 into 10 power 10, which gives you some value 3.19 into 10 power minus 3 gram. So this is your final answer.
Okay, another very simple problem, the problem of conversion of graphite into diamond. So you already know that graphite to diamond is not really feasible, right? You already know that graphite is the most stable form. It has the zero formation of energy and so on. That is already clear from the problem statement. But let's see how we can calculate the reaction constant, and that will also tell us that this is not a feasible reaction. Okay, so what do we have here? Delta G of reaction. This is what we need to calculate. That would be delta G of diamond minus delta G of graphite. Okay, so these values are already given. You will see that this is 2.9, so plus 2.9 kilojoule per mole, right? Because for graphite it is 0 anyway. And then how do you calculate the reaction constant K? That equals E power minus delta G by RT. So just keep in mind the units and you should be fine. This is a very simple problem. So minus 2.9 into 10 power 3, it is kilojoule, divided by whatever is your universal gas constant and the temperature in Kelvin, and this will give you a value which is approximately 0.278. So this is basically the solution of the problem. You just need to see that the delta G of this reaction is greater than 0, so it is a positive value, and now you also see that the value of reaction constant is smaller than K, which, so both conditions suggest that this is not a feasible reaction at standard room temperature and pressure. Not feasible. Okay, so we are done here. So this is the numerical problem on the CVD reactor. What do we need to calculate here? We need to calculate the boundary layer thickness, which is equal to delta. Delta equals L, which is the length of your substrate, divided by the square root of Reynolds number. So first we need to calculate the Reynolds number, which is nothing but rho V d by mu. So all these values are given to us. Rho equals 0.658 kilogram per meter cube. And what is V? V equals 10 meter per second. What is D? Equals 1 meter. And mu or viscosity is given to us as 0.55 poise, which equals 0.055 Newton second per meter. Okay, so now from here I have calculated the value of Reynolds number as 119.63. You can also calculate it for yourself. And once we have the value of Reynolds number, now boundary layer thickness is very easy. L is given in centimeter. Okay, I can just leave it in centimeter because it doesn't matter. Reynolds number is a dimensionless number. So if I take it, if I take my L value in centimeter, then I'm going to get also the boundary layer thickness in centimeter. So from here, what I get is 0.1828 centimeter. So that is basically my final answer. Okay, so this one is a very simple problem really. So you are given the energy that is required for cross-linking the film of your resist, okay, and you're given the intensity of your lamp. Now in general what happens is, well, you don't really know the energy in the beginning. In your whenever you're using a certain type of photoresist, then these resists will come with what is known as the data sheets, especially when we are talking about the negative tone resist. Then we often have data sheets that are provided by the vendor, and in that data sheet you will often have this information for which thickness what is the energy that is required. So for example, for 20 to 40 micrometer for any given resist, there may be, let's say, 200 millijoule, and it can be, so for 50 it can be different, and for 150 micrometer it will be different, for 5 micrometer different. So you have to first learn how to read the data sheets, which is not very difficult. So from the data sheets you can figure out what is the energy required. So here I have already given you the value of the energy for cross-linking, and now What is your lamp intensity is also given, but again, in the clean room, what you may have to do is there are intensity meters which you need to use to get the value of the intensity at that given point, because often when you buy, for example, mercury lamp for UV exposure, over time their intensity decreases. So at any given point, what is the intensity? The best option is to measure it on that day just before your experiment. Okay, so if these are the two values and you need to calculate what is the exposure time, well, since everything is given in nicely in the same type of units, in centimeters square and also millijoule, milliwatt, all you need to do is you just need to divide your energy by the intensity of your lamp. That's all. So basically this comes out to be something like 24.39 seconds. So since you cannot expose for 24.39, you will expose it for 25 seconds. Okay. Now here a few more important things which I have not mentioned in the question, but I should tell you. I told you that this experiment is being performed on silicon wafer. So that is also I have written for a reason, because if you don't have silicon substrate and you have silicon oxide substrate, or let's say you're not making this entire structure on silicon at all and you're making it on a glass or quartz substrate, or there can be other substrates, sapphire substrate, you can choose different, even ceramic substrates for certain applications. In that case, you need to also see if your resist requires the same kind of energy or different. You have to factor something else in. So for example, often in the case of glass, you require 1.5 times the energy that you require for silicon wafer. So this is also, these kind of things are also mentioned in your data sheets. So you can then, you definitely need to check for all these things before you calculate your exposure time.
Okay, so now we come to a manufacturing related problem. So you can see in this problem, I have given you a certain shape, a certain cylinder of graphite, and you have to fill some iron inside it. And then there are some other parameters that you can see in this problem. Now, the thing is, this is one structure and it contains 3 different types of carbons. So you have, graphite cylinder, and then you have HOPG. And then you also have some low purity carbon, and then of course some other metals and so on. So how would you go about making such a structure? So let's solve it.
Okay, so how do we go about making this kind of cylinder? So first of all, we need this hollow cylinder, right? And inside that we need iron filling. So the first thing that comes to your mind is we can perform casting for filling the iron. Okay, you can also insert an iron rod, and either way, what you would need is first you would need your hollow graphite cylinder. Now I said casting because graphite itself can serve as a refractory material. What does that mean? It does not lose its any properties or its mechanical strength at high temperatures, even at very high temperatures. So we can have the hollow cylinder made of graphite. So that is going to be our first step. We manufacture the graphite cylinder itself. Okay, and how are you going to do that? Well, you have learned a few techniques for that. Also, you know the precursors. For example, you can make it using needle coke, or you can make it also using some other polymer, for example, PVC. And well, this is the most common one would be needle coke plus say either a pitch or resin binder, and then basically you will heat treat it. So this you can see in the needle coke lecture. So you will first heat treat it at lower temperatures, say 1000 degrees, and then you will have to perform the pore filling operations, and finally you have to go to very high temperatures, let's say 2600 degrees Celsius, for getting the graphitization. Okay, so now what you have your cylinder ready. So this is your hollow cylinder. Okay, and then you have this some hollow structure. So this is the structure that you have now made. Okay, so I can also cover it here. This is your front view of a cylinder. Okay, so what is next? Now you need to fill the iron inside your, so this is where you need to now have your iron filled. Okay, so what can you do? You can actually just, so the second step can be casting of iron. Okay, so you can perform the casting and you now have your cylinder also filled with iron. Okay, now what is the next step? Next step you need to do is now you need to make the top layer. So top layer, if you remember, that top layer needs to be graphite layer again. However, there should be some metal layer in between and we can choose any metal for that purpose. Okay, so let's say here I need a metal layer. Okay, so what do I do now? The top part looks like HOPG, right? So this is some, because we have 0.8 degree of mosaic spread, and this is the HOPG part. And for making HOPG, the standard process is basically pyrolysis of a hydrocarbon. You can also call it a CVD. So basically this is a pyrolysis of hydrocarbon. So this is our step number 3. So this is for making the top layer. Now remember that before we make this, before we perform the pyrolysis of hydrocarbon, what you anyway require is a catalytic layer. So this is similar to what you have for graphene CVD. So you have a copper layer, or you can also have a nickel layer, depending upon how much what you need from your what thickness do you need. So typically we would take nickel layer, because copper layer tends to have only a few layers of carbon deposited, right? So now we take the nickel layer, and then on top of that, now you pyrolyze your hydrocarbon. One important thing is that when you want to convert these hydrocarbon layers into graphite, you cannot really anneal out the entire structure at very high temperatures, because in the question it is mentioned that your iron should not be heated above 900 degrees. Okay, so what else I can do? What I can do is I can perform hot pressing. So rather than annealing out the entire structure, so let me call this 3A, and this is my 3B step. There I will perform hot pressing, and then I will go above say 2600 degrees centigrade, very similar to the graphitization temperatures. So then I get my top layer. Now we are good. Now all we are left with is the bottom carbon layer, and bottom carbon layer can basically be porous and low quality. That is what is mentioned in the question. So what does this mean? Well, porous low quality carbon we can basically make at temperatures as low as 900 degrees. So that is your in fact also, then we don't destroy or we don't harm the iron, because it should not go above 900. Okay, so you will take any polymer which can, well, if we need intentionally, we need the porosity, then in that case we will take any polymer which goes through charring process. However, if your question says that, well, porosity is acceptable, in that case you can take any polymer. But okay, since we have specifically mentioned that there should be some porosity in the structure, then we will take some polymer which undergoes charring, for example some cellulose or something, and then heat treat it at 900 degree centigrade, and then what we get is some low quality, so basically low purity carbon with some porosity. So this is your low purity carbon which we can get at 900. So that is basically it. That is your entire structure.
Okay, yet another problem related to making carbon structures. But here we will be talking about how to make structures from polymer to carbon. So basically, how do we optimize? How do we come up with the exact dimensions of our precursor material? So I have not gone into the details of how much shrinkage your polymer has, because in this problem you can already see the shrinkage parameters are not provided to us. What we just need to find out, at what dimension do we get porosity free structure. So I think this problem I had also mentioned in one of the lectures, but now when it comes to manufacturing, maybe you will understand a little more details when we solve it again now.
Okay, so this problem looks more complicated than it is. Actually, I've written a lot of story in the question statement. Basically, the question is, if you don't know anything about a polymer, you just go to the market and you purchase a certain polymer, or let's say you buy a new equipment which comes with its own polymer. So for any given reason, if you don't know anything about the polymer, then what can you guess about these structures? And say you can only fabricate at 900 or 1000 or whatever certain given temperature, and you have certain capabilities of your equipment, of your furnace, and then you need to find out whether or not I will get porosity free carbon. Okay, so whenever we make any structure, what happens is, let's say when I have this structure, now, some parts, so the parts, let's say, some parts which are closer to the surroundings, they get heated up, and they start to become carbon. They start to, get carbonized, and this process continues. But you should also know that the material which is in the middle, this material is still sort of, it's not completely carbonized yet, and it has a lot of bubbles trapped inside, and because there are a lot of gases being produced, and those bubbles will need to get out, and they are still far from the surface. So they find it difficult to anneal out. However, the bubbles that will be forming here, near the surface, they will anneal out quickly. So that is basically your problem. There will also be some thermal conductivity difference, because this material is already carbon, let's say at a given temperature, while this material still contains a lot of tars and bubbles. So of course, there is going to be also a thermal conductivity difference. So the temperature which is reaching the core of this structure may not be the same as what you have on the surface. So due to all of these things, what you will have is, often the core remains, let's say uncooked, while the surface gets cooked. Okay, so this is the problem. What do you do if you are given any polymer? So whatever I have asked in the question, what you can actually make, is something very simple. You can make, a wedge-like structure. Okay, like a piece of cake. So say this is your structure. So this is your wedge. This is the top view of your wedge. And now you just heat it inside the furnace. So I said that you should design one experiment, whatever is the temperature you want to use. Let's say 1000 degrees centigrade. Okay, so now you place your piece of cake inside that 1000 degree furnace, and what you will now get is some part which still contains porosity. So you can see, because of this wedge-like structure, the thickness of the end of this wedge is much smaller compared to what you have over here. So basically, due to this gradual decrease, there will be some point where you can now slice your, basically now afterwards, after you remove it from the furnace, then make a lot of slices, very thin slices, and there will be a certain point where you will be able to see, some porosity. So basically, whatever is the length at this point, that is the maximum dimension you can get. So this is basically a rather simple problem. Okay. Now coming to the second problem. So this was the first one, and second problem, that is also very similar. Basically, I have just asked you, how do you know if a polymer is going through coking or charring? So coking and charring, this is again something that you have to often experimentally figure out, especially if you don't know anything about the polymer. Okay, so what you can do is you can make structures that can potentially bend. So say I think I had also shown you some figures which look like this. So this is a cone. Okay, so you can make these cone-like structures using your polymer, and then let's say this is my silicon substrate. Now when I place it in the furnace, I can place it like this. Okay, or I can place it also like this. So this being my sample holder. Okay, so I can place my structures in different ways if this structure does undergo coking. In that case, after the pyrolysis, you will find some sort of bending. Okay, or even if the polymer, if it goes through too much of a liquid state, so not a semi-solid but rather a a viscous liquid type state, in that case, even when your tip is standing up, you will find some sort of bending. But if that is not the case, because in most cases, there are many polymers, they just go through a rubbery or semi-solid, whatever you want to call it, rubbery state, not a liquid-like state. So in that case, what you will need to do is you will need to perform, you will need to place your sample in such a way that you can, observe some sort of deformation afterwards. You can also make structures where, for example, I make, two pillars of carbon or polymer, sorry. And then on top of these pillars, I place another, say, either a thick fiber or some other structure, all of it, let's say, so it's a ribbon-like or a thick fiber-like structure. Now what will happen? So this is the top view, so this will be the side view. You have two pillars, something connecting them. This is the side view, this is top view. Okay. So in that case, what will happen is, when afterwards, after your pyrolysis, because your pillars are also shrinking, right? Then they will have some deformation. Either this structure, this fiber or ribbon or strip, whatever you had, this will get elongated. So this is also one more thing that you can do. Instead of this fiber, you could also have made sort of an entire wall. It depends, of course, on your fabrication capabilities, but if you make a wall between these two pillars, in that case, your wall may also be deformed afterwards. You can also make structures where you have, which are being pulled. So let's say this pillar is connected to another pillar here, and this pillar in another direction is connected to something. So basically, during the shrinkage, pyrolytic shrinkage, this pillar will be pulled in this direction, the other one will be pulled in this direction. In that case, your wall will be, twisted. You will get something like this when you get the top view afterwards, after the pyrolysis, and then you have your pillars. So basically, these are the kind of structures you can. The idea is to make non-uniform stresses or structures which will, after shrinking, undergo non-uniform stresses, and then you can accordingly study the deformation behavior. If you do see deformation but a continuous structure, so this is your polymer, let's say your wall became like this, but it did not break, or your whatever was the fiber, it got pulled but it did not break, it just became thinner. In that case, this is your coking process. If you have a polymer which, rather than twisting or bending, it breaks. So if you had a charring kind of mechanism, then let's say whatever was your fiber, that breaks. Or whatever, if you had the wall, it does not really show bending, but two separate structures like that. So if there is any kind of fracture in the structure, in that case you can say that this is your charring process. So basically, these are some of the simple experiments that you can perform.
Okay, finally, we solve a couple of problems related to the characterization techniques. Again, X-ray diffraction, we had already solved one problem when we were discussing the lecture. And now, also, I don't remember, but maybe I did tell you a few things about the Raman spectroscopy, and also definitely we discussed when it comes to TEM images, how to, correctly interpret them. But these problems will probably also help you, because these are more related to, the practical problems that you will face during making something using carbon. So for example, the first one is on Raman spectroscopy. Raman spectroscopy, that is used for, at different temperature points, as you increase the graphitic content, for example, in a graphitic carbon. Graphitic carbon can be graphitizing or non-graphitizing type. When we say graphitic, now you know the definition of graphitic anyway. So here, using the Raman spectra of the same carbon material at 3 different time points or temperature points, how do we determine if at all there is any increase in the graphitic content? So that is your Raman spectroscopy problem. And the TEM problem, that is very simple. you have an intensity profile, and now you need to find out whether or not you have, what kind of stacking do you have in your carbon material.
Okay, so I have again pasted all the Raman spectra here. So this is some carbon material. Let's say it is some sort of disordered carbon material. We get it from polymer, and we keep on heating it, say at 900 degrees centigrade, and then at 1000 degrees centigrade, and let's say this one is at 1100. So we need to find out what is the optimum temperature, or if there is any increase in the graphitization or the graphitic content in our carbon material. So can we do that using Raman spectrum? Okay, so we know that from any standard, most of the disordered carbon materials will have this kind of Raman spectrum, and they will have two bands, D and G band. Okay, so we are not talking about graphite. So as you can see in the spectrum itself, this is that of a disordered carbon material. Okay, fine. So now one standard method for finding out what is the change in the graphitic content is to divide the intensity ratios, intensity of these peaks. So ID by IG. You can also do it the other way around, IG by ID. But you should know that this is for the top one is for the, or this one is when you write D, then this is for the D peak, and G is for the G peak. And when we say intensity, so often people would measure just intensity. Intensity means just say this height, in both cases. So that is your intensity. But in principle, because your peaks are merged, so what you have here is not really two clear peaks, because your D peak can basically, it can also be like this. So we also saw this in the class, and then your G peak can also be like this. So you will have, two different peaks, and what you need to do is, if you want to get more accurate information, in that case, what you should do is you need to fit these peaks, and you need to find what is the actual area of individual peaks. So rather than intensity, or rather than just the height of the peak, what you would rather calculate is the area of both peaks. So basically it is your area of the D peak divided by area of the G peak, but we will still consider it, or call it at least, ID by IG ratio. And this ID by G ratio will keep on either increasing or decreasing, and depending upon that you can figure out what is your increase in graphitization. So in this case here I'm not really able to calculate the area of each peak, because you will need to find actually the best fit. So you might indeed have 2 or 3 different types of values, and you need to find the best fit value. And in that case you will find this using this formula. You can find if the ratio of the G is increasing. If the intensity of your G peak, intensity or area is increasing. So ratio might be decreasing if you're taking ID by IG. Okay, and so in that case, you can either you can calculate it using the intensities, the heights of the peaks, or the area of the peak, and then you can find out your ID by IG ratio. Typically, within a certain range it will have a linear increase, the ID by IG ratio, and that linear increase will tell you whether or not you have more graphitic or more disordered content. However, if the disorder increases too much, in that case you may not get a linear increase. So remember that. But for most practical purposes, this method is very useful, and this is how you calculate it. Okay, so again, I have pasted the same intensity profiles here. What do you see here? Okay, you see that there is some value 0.33, 0.35, 0.35. So the first 3 values are actually, they look like they might be the values for some sort of graphitic carbon. So you know that for perfect graphite you have 0.335 nanometer, and so all these values are in nanometer. But you will get values up to 0.36 or even slightly higher. Even then it is acceptable. in the in the case of disordered carbons. Now, why I'm saying so, if you remember that turbostratic carbon, disordered carbon, at some point I told you that 3.44 angstrom or 0.344 nanometer is the limiting value. Well, first of all, that value has also been debated to some extent, and it is acceptable that up to 0.36 nanometer you can still call it disordered, or you can call it turbostratic carbon. However, there is also one additional factor. When we are doing these manual calculations of the distance between the two intensity peaks, in that case also there is some manual error, or there is a possibility of manual error. So in that case, let us say up to 0.36, we just call it okay, acceptable in your graphitic carbon, or at least graphitic turbostratic carbon. So when I say graphitic, that means that this is an annealed carbon. So graphitic, turbostratic, so basically annealed at, say, high temperatures. This might be your, say, glass-like or activated carbon sample. Okay, so now these three, the first three values are acceptable, but the after that you have 0.38, 0.42, and 0.38. So now these values don't look like the values of even an annealed carbon. What does that mean? Of course, these values, the intensity profile was taken on your annealed carbon sample. So that basically indicates that it's not that this is another material or impurity or something like that. What it indicates is that you're not looking at the side view of your stack. So let's say if I had my stack like this. So for the first three values, say it is 0.33, 0.35, 0.35. So in that case, I would assume that I'm looking at the the cross section. So let's say this is, now when I say the first three values, then I'm looking from here. Okay, but when we see the other three values, it is quite possible that we are looking at some sort of top view. So it could be something like this. And now we are looking from the top. Okay, so this is also possible, and that is the reason the values that you're getting, let's say what you're getting, this distance here may not be close to the distance, then this can be 0.4, it can potentially be anything. So this is one possibility. Another possibility is that what you have here is, then after three layers, what you have is probably a lot of defects, and you have these because of the defects you have more spacing between the layers. It can also be some other layers coming from a distance, and then these values here, then these values are some random values, but in some region you can say that there is a little bit of graphitic content in your carbon material.